Okay, we are going to talk about electrochem now. And so this is going to be chemistry with electricity. And so the first thing I want to talk about is electricity itself. Anybody want to give a quick, this is what electricity is? Flow of electrons through a conductor. Like that, there isn't anything else to it. Electrons flowing through a conductor. When you plug in, so this cord right here, when this guy gets plugged in here, why did that turn off? That was annoying. Why did the external display disconnect? Okay, share. Maybe that thing needs power to share. All right. So I'll pick another one. So these cords right here, where's the electricity coming from that powers this? Second. Coming from an outlet. Coming from an outlet. So the outlet just is a magical source of electrons. It's kind of weird to think about. Where does the electricity come from? Like, how do we generate it? So we generate three different ways. In our society, we use three different ways to generate the electricity. Actually, four. We have the regular way, which is using a generator. We have batteries, obviously, and then we have solar, and then we have fuel cells. So those four ways are typically what we use to do this. Do we know how the regular old generator works? Around inside, surrounded by windage. Yeah, that's fantastic. I didn't know it was going to come through that. That's kind of cool. I mentioned this once before. This series of, you're not going to make me buy this, are you? Do we know what this cartoon is? It's called Schoolhouse Rock. This is what was displayed as like a public service announcement for little kids on Saturday mornings when parents were sleeping and the cartoons were on. And so this was actually a fantastic way to show what electricity is, and it's super correct. So those wires, those things are large, they're girthy, they're very heavy. You see them right over here on the east side of the Dalles, that section that comes up from the dam and then goes up to the hill there, that's called Big Eddy. That's the substation. So in this case, we've got a coal fire plant, so they're burning coal to heat water. Water boils. The steam is used to turn a turbine. So what we're trying to do is turn something, and exactly what Ben said, we are trying to turn this thing. And so there's different ways to do it, but back you up right there. So what we need is a magnet, a current carrying conductor, and relative motion between the two. So we've all seen a horseshoe magnet before. So if I take a metal hanger and a horseshoe magnet, and I just pass the metal hanger through the horseshoe magnet, there will be electricity generated at the ends of that hanger. That's literally all you need to do, a magnet and a wire, and then motion between the two. So in this case, what we've done is we've placed wires along this shaft, and inside it, or on the outside of it, I've got a powerful magnet. And so as this thing spins, those wires pass through the magnetic field. That's how we typically create electricity, whether it's the dam or a coal fire plant, natural gas plant, nuclear power plant. All of these things are doing the same thing. They're trying to spin the generator. So when this generator spins, the electricity pops out of this. So what do we use to spin the generator? Obviously, we use the river. It would be nice if we just had like some Hulk people hanging out in generators, spinning them. At Oregon State, the gym, the treadmills and the bikes, they actually back source the electricity. So as you're pedaling, you're creating electricity, and so they supply it back to the grid. So during like high use times in the afternoons and in the evenings, the student union actually makes money from all the people riding bikes and whatnot. I don't know if you know this, but the guy who came up with 5-hour energy, 4-hour, is it 5-hour energy? He's a billionaire. 5-hour energy, he's got like $4 billion. And he was never expecting it to take off like that. He thought, you know, he could just have this little business and not be a big deal. So now he's like trying to give back. And he has created a little bike thing. It's not actually little, it's actually tall. It's like 10 feet tall. And you just sit and pedal it, and what it does is it allows you to power a generator or power a battery. And so these people that are in remote areas can have this thing just set in their village, and people can take turns pedaling on it, and it powers this battery that can power essential services, communications, lights. They use them for remote hospitals and whatnot. So really all you need is wires, a magnet, and then somebody to move the wires through the magnet, or somebody to move the magnet around the wires. That's it. So that's all we're trying to do with this electricity. So we're trying to get these electrons to flow through. And the interesting thing about this is the electricity that's coming out of this extension cord that's plugged into that wire, the electrons that are powering this screen came from that dam. They're actually in physical contact with each other. They're the wire that hits that goes to another spot, goes to another spot, goes to another spot, and they keep coming in. They're all basically touching each other. So the electrons that are flowing through this came from the dam. The electrons don't like instantaneously move from the dam to here. It's more like the way trains work. When you move the front car of a train, the back car moves. So they're sort of like get pushed, that Newton's cradle thing, where you like grab the one and it hits the side and then the one on the other. That's really what's going on. So the electrons that are flowing through here left the dam a long time ago, hours ago, and now they're finally just making it through as they get bumped and bumped and bumped, and they shuffle their way along. It moves at about 2 centimeters a second. So, I mean, that's not very long. It's basically an inch, a little less than an inch per second as the electrons are moving down the wire. But it feels like it's instantaneous because the moment one gets bumped, all the rest of them in the line get bumped. And so the instantaneous feel is basically the Newton's cradle effect. As the electricity that we typically use that comes out of these LEDs is about 110, 120 voltage. And the current that comes out of the wall, or that these can usually handle, are 5, 10, maybe 20 amps. So those are the two units that we're going to be focusing on. One of them is voltage and one of them is amperes. Voltage is sort of like the pressure of the electrons, and amperage is how many electrons are passing a point in a given period of time. So if there's a lot of electrons, then more work could be done, but maybe not if the electrons are weak, as opposed to having fewer electrons, but those electrons have a lot more push. So in your house, you basically have two different voltage systems. One voltage system is the 110, 120 voltage system, and the other one is the 240 system. So obviously the 240 system, that's double your 120 system. So what kinds of things get powered by the 120, and what kinds of things get powered by the 240?
240 is your dryer, your water heater.
Maybe your
air conditioning.
Furnace, AC, those things usually run off of, if it's like a central air stuff, then the AC will be on that. So You usually have 2 or 3 things being powered at 240. You might have gas for everything, and then you don't even have a 240 system. You'll have a breaker at the box because it's code, but then it never gets used. But if you're running an electric dryer, I mean, you probably have seen that. You can just plug the washing machine into a regular spot, but the dryer has to get plugged into one of those weird outlets, and that's 240 volts. So the electrons that are coming to power the dryer have double the push. And because the conductor is really big, you're rest assured that there are also a lot of electrons. It just takes a lot of energy to tumble, and really almost all of the energy from the dryer is used to heat it. So if you just tumbled your clothes with no heat, you wouldn't need a 240 volts. It would be easy, but they wouldn't dry very fast. The voltage that's running through the power lines around like above the house, it's probably going to be double the 240, so 480, or it could be double that. It could be 10, 20. So those lines that are running through are much higher. And when they use, I'm sure you've seen those cylinders that are on the power poles. Those cylinders actually step the voltage down. The voltage that's running up from the dam all the way up to this Big Eddy thing, that's probably 4,160 volts. But then when it gets up to Big Eddy, it gets jacked up to like 20,000 volts. And then almost all of the electricity that's generated by that dam ends up in Los Angeles and San Francisco. That's what all of those power lines that are going all that way down there. If we cut those power lines, they have 19 functional turbines at the dam. We would maybe 2. Well, actually, no, Google's here now. So it would probably be more like 4 total. But all the rest of them would sit idle because this area can't use all of that electricity. So when they built the dams, it was understood that obviously it would power local stuff, but most of the electricity would go to other places south that need the electricity more than we do because of the higher populations. Why do they jack the voltage up to 20,000 volts? It's much more efficient. And so this thing right here, there's a third part of electricity, and the third part of electricity is resistance. And so I'm not sure why, but I is the symbol for current. So the amount of electrons that flow through a wire. And so what I want you to be thinking about is as the electrons are flowing through a conductor, they actually produce kind of like a friction sort of effect. And so the friction effect is I squared R. And so that's whatever the amperage is, square that, and then multiply by the resistance of the conductor. So if the conductor has any sort of resistance, then you'll end up producing a bunch of heat. Sometimes we want that. The burner on top of your stove is just a medium resistance material. We run electricity through it. The electrons actually have trouble traveling through the burner on top of the stove. So they produce a lot of these things called I square R losses. So in the same way you get friction by rubbing your hands together, the electrons passing through a resistor produce heat. And so that's, all the heat stuff that we've got, the furnace, your electric water heater, all of those things are just a piece of metal, alloy, graphene, some other stuff mixed in with there, and it purposefully causes friction. And that friction is turned into heat, and then we use that heat to heat stuff. It's actually much more efficient than the gas stoves and gas furnaces, the electricity. All right, so generally we don't want any resistance in our electrical circuits. Like in this cable right here that's powering my laptop, I want this to be as friction-free as possible, because if there's a lot of friction in here, then this wire gets warm. And 2 bad things with that. If the wire is getting warm, that means that whatever I'm using the system for, to power a laptop, to power a light, to power a TV, is being stolen and turned into heat. And I don't want that. I want it to, do whatever it is that I want it to do. And the other thing is, if this wire gets too hot, what might happen? The insulation will melt off, and then the 2 wires will touch. And if the 2 wires touch, they will cause a fire. So why are there 2 wires? Or in this case here, there are 3 wires. One wire has electricity going to the something. one wire has electricity coming back to wherever it came from. So the electrons that are running through this TV came from the dam. They go back to the dam. If I open up the circuit so they can't get back to the dam, then the whole circuit stops. It doesn't matter if all the connections to the TV work. If the connection back to the dam is open, it turns off. It can't move if there isn't a flow back to where it came from. So all this electricity needs I start with a place and then I need to end up at that same place. So I end up just going off and doing something and coming right back. It's I mean, it's an electrical circuit. So the circuit means I go off, I do some stuff, and I come back. Just like if you're over at Cirrhosis Park over there, there's like a workout circuit. You start here and then you run to this next spot and you do this next thing and you do this and you work your way around the park and you end up at the same spot, your circuit. So what we don't want is we don't want too many electrons running through a wire that's not rated for it. And so if you've got, if you plug a whole bunch of stuff into an outlet and it blows, the circuit breaker blows, that means you've got too many electrons coming through that wire. So you need to either have that whole circuit upgraded. So they'll actually come in, change out the wires and make them bigger. And then it would work. Or you could, obviously plug stuff into another wire. If you were to look at the circuit breaker boxes at your house, most of them will say 10 or 20. The one going to like a furnace or a hot water heater might say 60. And so that's the number of amperes that'll go through there. Your car circuit runs off of batteries and an alternator, which is basically just like a tiny generator. And that whole system runs off of 12 volts, as long as we're not talking about an electric car, not the motor part of it, but just 12 volts. You would need the minimum voltage to electrocute somebody, and by electrocute, I mean to get somebody's heart to stop, is 36 volts. But 36 volts will only do that if the person is like sopping wet in salt water and they're sick. I know it doesn't seem like it would matter, but it actually does matter. If they're not sick, then it's more like 55 volts. And we know this because the Navy extensively tested humans and electricity. Like, hold this, get them soaking wet. All right, no, got to get it a little bit higher voltage, a little bit higher voltage. So if you just open up the hood of your car and grab the terminals of the battery, since they're 12 volts, nothing can happen. That voltage is, I need a conductor, and you're not a very good conductor. If you were to take like a wire and go from one terminal to the other, you would melt the wire immediately. So many electrons would go through, but you're not a especially good conductor, even soaking wet in salt water. So, yeah, my best analogy for the electrons is sort of like a water. You can have the electrons moving with very high flow and very low pressure, or you can have them moving at very high pressure and very low flow. I mean, if you stand in the Columbia River, you're getting hit by a ridiculous amount of water molecules. But I'd rather do that as opposed to standing in front of a pressure washer, or even just like the pressure washer thing that they've got at the car wash. Like that would hurt. Even though the number of water molecules are so much smaller than the river, they're coming out a lot faster. So the speed, sort of the pressure is sort of the voltage of it, and the quantity of molecules and electrons, that would be your amperage part. The symbol for voltage is V. The symbol, it can be E sometimes. The symbol for I is amperes, and the symbol for power is P. It's kind of hard to think about our lives without electricity. Like, people living out where there isn't any electricity purposefully. It's a weird thought process for us for these last 100 years of what we've done and how much we rely on the electricity itself. There's not a lot that you do that electricity hasn't impacted in some way. Like if the electricity, like if all the power in the gorge went out, like what kinds of things would change in your life? The answer would be pretty much everything. Maybe a wood stove. That's about your only way to keep yourself warm. All right, so we're gonna focus on batteries for this section. How many batteries are you using in a given day? I'd say at least two on any given day, because you're probably walking around with your phone. So obviously one, you're probably driving, so that's definitely two. Although if your car has been made in the last 30 years, it has multiple batteries in it. There's a important engine computer battery that like remembers all the tuning agents associated with it. So, but at least two. What are your other two, Grayson? Yep. So, I mean, my laptop, even though it's plugged in, has a battery in it. This mouse has a battery in it. I mean, we're sitting, we're in this space, not particularly, but your house, you probably have batteries in your smoke detectors. Maybe you've got a little shop vac or something like that. Batteries in that, obviously. I mean, they're perverse. They're everywhere through society. It would be difficult for us to get away from batteries. And now that we're building automobiles using batteries, it's only going to be more and more battery stuff. Okay, so what is it that the battery does? How does the battery work? So when we're talking about batteries, we're talking about a redox reaction. So this is taking us back to Chem 121. A redox reaction is an oxidation reduction reaction. So what happens with an oxidation reduction reaction? You get one thing that is losing electrons and one thing that is gaining electrons. So if I just put up something super simple, like I've got some charcoal, charcoal reacts with oxygen gas to burn to make carbon dioxide. All right, super easy. So this is an element in its elemental state, so its oxidation state is zero. This is an element in its elemental state, so its oxidation is zero, meaning the carbon has 6 electrons to go along with its 6 protons, and each of the oxygens has 8 electrons to go along with their 8 protons. So I put them together, and that is not what's happened on the other side. What's happened on the other side is I've got a carbon, it's doubly bonded to oxygens on each side. This carbon's charge is now +4. This oxygen's charge is -2. This oxygen's charge is -2. So tell me what happened. Between the carbon and the oxygen, what occurred? You want to reverse that? What's +4 next to the C mean? No, no. The proton's charge is plus, right? The carbon always has 6 plus charges because it's a carbon atom. If its charge is now +4, it doesn't have, over here its charge was 0, right? So it's got 6 protons and it's got 6 electrons. So over here, after the reaction has occurred, it still has its 6 protons because that number can't change in a chemical reaction no matter what. But since its charge is now +4, it lost 4 negative charges. So now it only has 2 electrons. Do you remember that? I mean, does that make sense at least? Its charge is +4. The only way it can be positively charged is it lost electrons because it can't gain pluses. So tell me what's going on with the oxygens. Every oxygen has 8 protons. How many electrons does this oxygen right here have? 10. We're not talking about, there isn't any sharing occurring per se with this. Let's just look at the oxidation states. So the charge is -2. That's what its oxidation state is. And so if my charge was 0 up here for this oxygen, it's got 8 protons it has 8 electrons. They have to cancel out to get to 0. Down here, they don't cancel out. There's 2 more negatives than positives. The proton number can never change. So the only way to have a -2 charge is the oxygen had gained 2 electrons. So that's why we're at 10 electrons. We all right with that? What do you have a scrunchy face for?
Undoubting.
And we're okay with the carbon's charge now being +4? How did it become +4?
-2 electrons from 6 protons.
It gave 2 electrons to each oxygen. Each oxygen took 2 electrons away. Why? Well, whose electron configuration has 10 electrons? Neon. So it wanted to look like neon. Carbon is the, I don't care which direction I go. You could give me 4 electrons and I could become neon, or you could take 4 electrons away from me and I could become helium. I don't care as long as I become a noble gas configuration. So if I'm this, and this leaves me with 2 electrons. So my electron configuration here is 1s2. That's it. Well, that's neon. My electron configuration here is 1s2, 2s2, 2p6. That's neon's electron configuration. They're just trying to look like noble gases. So this chemical reaction produces energy. Are we okay with that? This is charcoal burning. So the process of carbon giving its electrons away and oxygen accepting electrons is an exothermic process, exergonic process. Its delta G is a negative value. It's a negative value. The states are all gases. This was by itself, this was by itself, and now it's mixed together. So I've increased the chaos and I've lost energy, lost H. So this reaction is very spontaneous. Okay, so the oxygen gained 2 electrons, and what happened to its charge? It went down, and so we say that was reduced. The carbon was oxidized. Why? Because it lost electrons. So if you lose electrons, you are oxidized. If you gain electrons, you are reduced. So if I look at this chemical reaction, the very first thing that we have up here, I have carbon with a charge of 0, and on the other side, the carbon's charge is +4. So the carbon is the thing that was oxidized. The oxygen's charge is 0 on this side, and on this side over here, it's -2. So its charge was reduced. All batteries are oxidation reactions. That's all they are. So all batteries are one substance giving electrons to another substance. And the other way to think about that is one substance taking electrons from another substance or accepting the electrons. So anytime I've got any kind of rusting, those metals are losing electrons, and it's almost always to oxygen because it's everywhere in the atmosphere. Rehashing this from 121. The reason that the loss of electrons is called oxidation is because every time scientists saw that substance was losing electrons, oxygen was doing it. So they had this assumption for a short period of time, but long enough for it to stick, that oxygen is the thing that steals electrons. And it does steal electrons. There's 2 reasons they thought this. One, every reaction that they saw did this. And the 2 reasons that that this was the case was oxygen is everywhere. And oxygen's the second best thing at taking electrons from stuff. Its electronegativity number is 3.5. The only thing that's bigger than the 3.5 is the 4.0 for fluorine, but there isn't fluorine just floating around in the atmosphere. If our atmosphere would be nitrogen fluorine, we would have called this fluorination, but there isn't any, so we call it oxidation. So for something to be oxidized, for something to lose electrons, it has to have electrons to lose. So if I'm talking about magnesium with a +2 charge that's aqueous, can this magnesium be oxidized? Can this magnesium lose electrons? All magnesiums have 12 protons. How many electrons does this magnesium have? 10. Can this magnesium be oxidized? What element on the periodic table has 10 electrons? So can I take more electrons away from this? You can't do it. That's why the oxidation states for column number 2, they're all +2, and there aren't any other options. So this magnesium has already been oxidized. It can't be oxidized further. There isn't a chemical out there that will take more electrons away, because what we've done is we've made this electron configuration neons, and neons is not reactive. What if I was talking about potassium? The 19 protons for the potassium, and this one has 18 electrons. Can I further oxidize the potassium? The answer is no. It's a column 1 metal, group 1 metal. Its oxidation state is 0 or +1. When I take 1 electron away and have 18 electrons, now I look like argon. I'm not reactive anymore. So this thing can't be reacted with. I can oxidize solid potassium. This guy has 19 protons and 19 electrons. It definitely doesn't want that 19th electron. It wants to get rid of it. So it's really easy to oxidize it. And you just expose this to the air and it'll rust itself before your eyes. You can see it go gray.
So for a substance like, I don't know, let's say iron. So you can get yourself some solid iron with an oxidation state of 0. If this is allowed to just persist in the air, eventually you're going to end up with probably Fe2O3. And that would be if it was mixed with oxygen. So this is just everyday simple rust. So what has happened to the iron? I started off with iron metal. And what did I end up with? Each one of them loses 3 electrons to the oxygen. So three oxygen atoms come over to 2 iron atoms. Each of the 3 oxygens takes 2 electrons away. The 2 iron atoms each give away
3 electrons, and then we end up with iron 3 oxide. This is normal rust. We could get it to rust in different ways, but under normal everyday circumstances, atmospheric temperature, atmospheric pressure, we're going to end up with this guy right here. And this is the rust that you see if you scratch your car. It's the rust you see if you get a ding on the wheels for your tire. There's a little spot of rust there. A little bit of rust on your bicycle or on a screw that's holding up a gate in your yard. Like, this is the rust that you're seeing. So what we're doing is electrons are going from here to here, right? All right, well, what was electricity? Movement of electrons, right? Well, what if we harness and direct the movement of electrons? We're gonna make a battery. So we've had batteries for an awful, I gotta back up one second. So who's oxidized in this last
reaction here. Iron became more positively charged, so it's oxidized. I like to think about it the other way when I'm looking at a reaction. Whose charge went down? Oxygen. So that was the thing that was reduced. So then the other thing was the thing that was oxidized. All right. So there's another way to talk about it. The other way to talk about it is agents. So you can have an oxidizing agent or a reducing agent. So this thing was reduced, and that makes it the It makes it the oxidizing agent. It is the thing that oxidized something else. And so this iron was oxidized. But it's also the reducing agent. So what does it mean to be a reducing agent? It means I have excess electrons that I can give away to somebody else to reduce that. You've probably heard oxidizing agent before. Under what circumstances are people talking about an oxidizing agent? Bad TV commercials? The OxyClean guy? So the reason that you would want an oxidizing agent in your detergent. So the detergent itself is really there. Its main purpose is to take oils off of clothing, put them into micelles and have them get washed away. But what if something on your clothes got stained? Then you would also want an oxidizing agent in there. And the oxidizing agent, what does an oxidizing agent sound like it does? It oxidizes something else. So if I've got a tomato stain on a shirt, tomato sauce stain on a shirt, the oxidizing agent will go in and take electrons from the dye that is staining the shirt. The stain is still there, but the thing that caused it to produce red color when light hits it is now been changed enough so it doesn't reflect visible light, doesn't absorb visible light. So that tomato stain or wine stain that was on your, white t-shirt or whatever can be still there, but chemically changed enough through oxidation so I can't see it. You would be able to see it if you use like a UV light, like it would pop up like a big bright light underneath that, but you wouldn't be able to see it under visible light. So the oxidizing agent has the ability to take electrons away from things, and within clothing and stains, when stuff loses electrons, it loses its color. Bleach is an oxidizing agent. Well, what happened if Ben were to put your jeans into the washing machine with a bunch of bleach? It changed color. And the color changes because the oxidizing agent of the hypochlorite goes in and steals electrons from the indigo blue dye. The dye is still there, but now it's been chemically changed to not absorb and reflect blue. Now all you're going to get is white, or maybe you use too much, maybe a tarnishy yellow color. All right, so we were talking about spontaneity, and batteries are inherently spontaneous. They need to be spontaneous. I need to be able to put batteries in something and then that thing run until the battery runs out of electrons. So all of these reactions that we're going to see will be spontaneous chemical reactions because the reactants and products want to do what they're doing and turn themselves into some other substance. Some battery names that I'm sure we know the lithium ion battery name. There's also nickel cadmium with nickel metal hydride. The nickel cadmium is what Toyota uses exclusively for all of its hybrids and electric vehicles. They don't use lithium. They have the nickel cadmium market is good. The batteries last a long time. They don't catch on fire when the battery is exposed to the atmosphere. So Toyota is just like, we're just going with nickel cadmium. We don't really care. And then the lead acid battery is the battery that you have that starts your car. Even in hybrid cars, because they have a regular motor, the starting of the vehicle is run off of a regular battery. Does anybody know what the cool thing is about having a hybrid car besides better gas mileage? How does the battery get recharged? It's a hybrid, right? I don't plug it in. So how does the hybrid car get recharged? All generators are motors, and all motors are generators. If you were to take, okay, so we all know what a box fan looks like, right? They're like this big. If you were to take like the cover off of it and hold the plug up and spin the fan with your fingers, you would create voltage here. If you spun it fast enough, you'd
create outlet voltage. You could literally power things at your house by just spinning the fan blade. The problem is you needed to spin at the correct speed, otherwise the voltage will vary. It wouldn't be a big deal if you were just trying to heat something, but if you were trying to run like a TV, it wouldn't work at all because the voltage would vary enough to either break it or for it to drop out from low voltage. But all electric motors are actually generators. It's just, do I put electricity in and make it spin, or do I put motion in and get electricity out? So the generator, the electrical motor that runs like a hybrid car, like the Toyota I drove here today, when you push on the brake, what it does is it makes the motor turn into a generator and it shoves electrons back into the battery. So the cool thing about hybrids is that car's 10, 11 years old. We've never changed the brakes on it because the brakes aren't really used. The car brakes itself by using the motor as a generator, and that takes energy to make those electrons come out of the generator. And so it just converts all the motion into electrical energy. The spontaneity of these battery chemical reactions will bring us to a term called active. And so active is how we'll describe metals relative to each other, more or less active than each of them. So some of the metals are much more active than other metals, and so we have come up with something called an activity series. Shrink this. Delete this. Okay, so this is an activity series. The activity series can be written a couple of ways. This is an oxidation activity series, which means it's written with the arrow producing electrons. So what's happened to each of these metals is they've lost electrons. It could be written in the complete opposite direction, where they gain electrons. The orientation won't change, it's just what's happening. Are they gaining or losing electrons? So here are a bunch of common metals on this list. Some things to note. This is an activity series, like I said, and the issue with it being an activity series is things that are higher on the list are more active than things that are lower. So lithium is more active as far as batteries go than, say, magnesium or iron. Platinum, mercury, silver, copper, all of those guys are at the bottom. So those would make bad batteries because they don't like to give their electrons away. Let's play a little which one of these is not like the other on this activity list. Hydrogen is a gas, right? And it's not a metal. So what's the importance of hydrogen on this list? Hydrogen is used as a standard for electricity. And then we measure everything else off the hydrogen. It's called the hydrogen cell. So for our purposes on this list, it means hydrogen, any acid can dissolve any of these metals, but not these metals. If I want to dissolve the metals below it, I have to mix acids together in special ways to make it so they're dissolvable. So if you mix nitric acid and hydrochloric acid, you can get it to dissolve gold, but neither one of them can do it on their own. So, I mean, what do all those things have in common at the bottom? We use them as jewelry. We use them as currency. Why? Because when I hand somebody a quarter, that person's not worried that quarter is going to dissolve at some point. It won't. But if I gave them a quarter made out of zinc, yeah, it wouldn't last very long, depending on what the atmospheric conditions are and how often it gets moved around. It would turn into dust after a certain period of time. It could be like in 5 minutes, or it could be in an hour. Could be in years, depending on how much activity it's got. So any of these things can be dissolved by hydrogen and those things there. These ones up top, they'll actually react with water. We talked about those. They'll produce hydrogen gas.
the water. If I turn it to steam, I can get more of them to do it, but the temp has to be much higher. And all of these guys, again, will react with acids and they'll
Produce hydrogen gas. So if you take just like a 16 penny nail, just like a regular old nail, and you put it in vinegar and you just wait, you'll see bubbles. The bubbles that you're seeing are a gas that's being produced, and the gas that's being produced is hydrogen gas. So what's that look like? Iron solid, here's my nail. I'll just put, I don't know, it doesn't really matter, hydrochloric acid, aqueous. It will make hydrogen gas, like I said, and FeCl3 aqueous. The hydrogen gas will be produced. This is a spontaneous reaction. It creates a little bit of heat and get a little chaos going here because the hydrogen is a gas. And so it increases the chaosness of it. That's not balanced, but it's not a big deal. All right, so the other part about this being active, let's go here. So this is the battery that Toyota likes to use, the nickel cadmium battery. So let's find nickel on this. Nickel's here and cadmium's right here. So which of those two metals is more active? The cadmium. And you can always figure out that the ones at the bottom don't react. So those are the least active, and the ones at the top are the ones that react the most. So if you're in the middle, just whoever is higher. So the cadmium is more reactive. So what's going to happen is the cadmium is going to be giving 2 electrons to the nickel. This is during discharge. And then the nickel will be giving 2 electrons back to the cadmium during charging. So again, it's just a cycle. The electrons go one place and then they have to come back to where they were to start with. So this is a little, this isn't showing you exactly what needs to happen. I'm going to start with cadmium, that's a metal. The nickel actually needs to have a +2 charge. Why am I writing no reaction for this next reaction I've written up here? The cadmium is more active, so it could give electrons to the nickel, but why is that one that I have an NR next to never going to happen? If this cadmium gives 2 electrons to the nickel, this guy would end up being CD +2, and this nickel would be Ni -2. Do you remember anything about metal oxidation states? They can't be negative. It's either 0 or it's positive. It's either given electrons away or accepted the maximum it can have, which is its proton number. So this reaction can't happen because the electrons need a place to go, and the nickel won't accept them if it's charged, if it already has all of its electrons. So this is the reaction that has to occur. When you have a charged up battery for a Toyota, all of the cadmiums have their electrons and the nickels don't have their electrons. Then the cadmiums give their electrons to the nickel, and we end up with CD +2 and Ni 0. And then The opposite is going to occur now that the nickel has all of its electrons. During charging, the charger will force the electrons off of the nickel and back onto the cadmium, and then we're back to where we were before. So when your Toyota hybrid is driving down the road and the battery is powering the wheels, this process occurring. The cadmiums are giving their electrons to the nickel. Then you jam the brakes on and the nickels give the electrons back to the cadmium. And this is how all rechargeable batteries work. I've got a metal with electrons and a metal without electrons, or something without electrons. The electrons go to the thing without electrons. The battery becomes depleted. I plug it in. The charger forces the electrons off the first thing back onto the next thing. So with this particular reaction, the nickel wants to give the electrons to the cadmium. The cadmium does not want to give the electrons to the nickel. So, the cadmium wants to give electrons to nickel. Nickel does not want to give them back. So nickel has to be forced to give them back. And that's what the charging process is. It takes energy to force the electrons off the nickel back onto the cadmium. So all rechargeable batteries, whether it's a nickel cadmium battery or a nickel metal hydride or lithium ion batteries, in the lithium ion batteries, the lithium has its electrons. Then as it's depleting its electrons, it's losing charge, and then I plug it back in and the electrons are shoved back onto the lithium. They don't want the electrons, but you can make them go back on with energy. So the discharge of the battery, whether it be your phone, this laptop, or your car battery, is spontaneous. The charging of the batteries is not spontaneous. So a spontaneous reaction might need a little jump start in the same way that I have to light some kindling to get a log to catch on fire. But once it's started, it's hands off. I don't have to do anything with it. And that's a spontaneous reaction. If I'm talking about a non-spontaneous reaction, it's not like I can take my phone, plug the charger in, and once it gets charging, I can unplug it and have it continue to charge. Because it's a non-spontaneous reaction. It's not like just get it going and it'll take care of itself. It needs constant energy input. Okay, and this is what you guys are going to do in lab today, or one of the things you're going to do in lab today. You're going to do an activity series. You're going to mix metals with salts and see what happens. And then you're going to actually create battery. So this battery, what we have here are a couple of beakers. So this is supposed to be a beaker here, this thing here. And then this one over here is another beaker. And this is a copper bar. And this is a silver bar. And so I also have this thing called a salt bridge, and we'll talk about all these pieces. So I've got a solution of copper 2 nitrate, and I've got a solution of silver nitrate. So inside here, inside this solution, I have AGs with a plus charge, and I've got nitrates with a minus charge that are aqueous. And over here, I've got coppers with a plus charge, and I've got nitrates with a minus charge. Okay. So if I looked at the list, copper is more active than silver, so it will give electrons to silver. So under what circumstances will copper give electrons to silver? What needs to happen? What's the starting? How does the copper need to start? It needs to be solid copper with all of its electrons. It needs to be an element of copper, and it's going to send electrons to the silver. So tell me what circumstance does the silver need to be in? It has to have a positive charge to accept electrons. And then when we're finished with this, we actually need 2 silvers. You're going to end up with a copper with a +2 charge that's now aqueous, and you're going to have 2 silvers that have a 0 charge that are now solids. So what's happening to this copper electrode here? It's dissolving. The copper atoms that are right here on the surface go from being copper metal to being copper ion, making the solution more blue. During the course of this battery's running, this solution here will become much more blue. And the electrons from this copper will get sent up, run through this voltmeter, come down this wire here, and then a silver that is sitting here will be attracted to that electron, and it'll start building up silver on the exterior of that silver bar. So the silver bar on the right is going to be getting heavier, and the copper bar on the left is going to be getting lighter. So the problem with this setup is I'm sending negative charges from the left side to the right side, which means the beaker would be coming on the blue beaker would be coming positively charged because I'm sending +2 coppers in. And I'm sending electrons over to the other beaker, and I'm pulling out those silver pluses. So then the right side would be coming negatively charged. So the way that we deal with that is I've got something called the salt bridge. It looks like a test tube with cotton in it, and inside the test tube, and then also the test tube is U-shaped. Both ends are open. I've got it filled up with a saltwater solution. And so what happens is when the copper comes in, this copper comes into the solution, a couple of nitrates from this potassium nitrate solution go in here, and they neutralize the charge. So when a +2 comes in, 2 -1s come in. When this +1 leaves and attaches itself to the bar, becomes 0, then a positive charge, potassium positive charge, has to go in to neutralize to make sure that the charge stays 0 on both sides. So the salt bridge is required to make sure that you have electrical neutrality. So how can this battery go dead? Basically 4 ways for it to stop functioning. The copper bar completely dissolves. Okay, what else?
The salt bridge.
The salt bridge could dry out, or the salt bridge could run out of ions, because so the salt bridge could fail. What about the silver on the other side? The electrons are going from the copper to silver ions. What happens if I run out of silver ions? Doesn't work anymore. I need a place for the electrons to go. So if you run out of these silver ions in this solution, there's nowhere for the electrons to go, so the battery stops. So if the copper bar corrodes away completely, or if all the silver ions in the solution on the other side are reduced, then it stops. If the salt bridge fails because it's run out of ions, or because it becomes dry, or the beakers run out of water, they evaporate off. So if you've got a battery that you bought a package of batteries that they've been sitting around, and you find them and they've been there for 8 years, and you put them in something and they don't work, why do they probably not work?
Can you repeat it?
I bought some batteries, put them someplace, and I forgot about them, and they've been there for 8 years. I go to plug them into a flashlight and they don't work. What has probably caused the batteries to go dead?
Evaporation.
Inside those batteries, there's moisture, and if that moisture evaporates, then the batteries won't work anymore. So if you want to keep batteries stored longer, you can put them in a freezer. The evaporation will significantly slow down if they're frozen. So what do you think about this battery? Is this a good battery? No, it's a terrible battery. The 2 reasons right off the bat that it's a terrible battery is silver's expensive, and copper's not as expensive, but it's still expensive. So I would never build a battery purposefully out of copper and silver. I'm just using this as an example. Also, they're heavy, right? Copper is dense. Its density is almost 9. Silver's density is like 11. I mean, those would be terrible metals to use. And now let's figure out what's the worst part about this? We'll come back to this. Sorry, we're going to go to here. So this is an activity series with voltages. So it's like the first one, but it's got more information. So we're going to find our silver. Here's our silver. And then here's our copper. This and this. All right, so these reactions are always going to be written in one direction. So what do I mean? In this particular one, the copper is gaining electrons and the silver is also gaining electrons. Is that what is happening in this battery? Only one of them is gaining electrons. So one of these is going to be written correctly and one of them is going to be written incorrectly every single time because it's always going to be written in one direction. And this one is this is a reduction one where they're gaining electrons. So the silver one is written correctly, right? A silver gains an electron, turns into silver solid. So that's going to give us 0.8 volts of electricity. It wants to gain that electron because silver is a metal that doesn't want to lose electrons. So if it's lost electrons, it wants them back. Well, copper is also one of those metals that doesn't want to lose electrons. But in this case, the copper isn't gaining electrons. So this reaction is written backwards, right? In our battery, the copper is the thing that's the reducing agent. So then I have to take the number that's written over here and write it backwards, negative 0.34. And then I could just volts, and then I can just add these things up. So 4.46 volts. So that's the third reason this is a bad battery. Its voltage output is crap. So when we're looking at this battery here, this is called a galvanic cell or a voltaic cell, because about the same time, two guys came up with this idea. We've actually had batteries for quite a long time, like before Napoleon kind of thing. We realized that you could produce voltages by mixing different metals together and different solutions together. And we've been improving on those for a while. This side over here is going to be called the anode because that's where the electrons are coming from. And this side over here is called the cathode because that's where the electrons are going to. Since this piece of metal here is getting larger, it's literally having silver ions attaching it to the exterior. We can do this and the metal doesn't have to be the same. So what I mean is I don't have to have a silver bar that's attracting the silver to it. I could have had iron in there, some other substance. And this is how we electroplate stuff. It's even how we electroplate plastic. So I'm sure you've seen some kind of metal coating on a piece of plastic before. This is how we do it. We literally run electricity to the exterior of the piece of plastic in a solution that's got metal ions, and then those metal ions stick. We usually use chrome because chrome does a good job of not oxidizing and is shiny. So how do you get a chrome bumper? I take a steel bumper and I put it into a solution with chrome ions and I run electricity to it. And then the chrome ions in the solution are attracted to the bumper and they stick when they get those electrons and it turns into chrome metal. So anything that's chrome plated, those are objects of probably the object that I use that gets plated probably has two properties. One, it's cheaper, but more importantly, it's probably more sound structurally. I'm not going to build mufflers and tailpipes for a Harley Davidson out of chrome, pure chrome. Why? Because the chrome itself is kind of a soft metal and isn't structurally sound. So it could easily be bent, nicked, bad things can happen to it. You kick it and you can bend the thing. But if the tailpipe is made out of iron, I'm not going to kick that and dent it. But it's also ugly and it's going to rust when it gets exposed to air because it'll be at high temperatures. So I protect the underlying metal with another metal over the top that won't rust under high temperatures in an oxygen environment, and it's shiny. So this is how we electroplate stuff. this is how I would write this in that battery up there in shorthand notation. So what I've got is the anode where I've got solid copper that turns into copper ion, a double line that's indicating that there's a salt bridge, and then I've got an ion of metal that turns into a metal element. So I start off with solid copper turning into copper ions, some other metals ions, in this case silver, turns into silver metal. So from this diagram right here, this little shorthand, you should be able to create this battery and vice versa. We don't change the voltages produced even if we have to balance the equation. So this is showing that the silver is gaining 2 electrons. I don't mess with it's still just 0.8 volts. I don't make it 1.6 volts. So this is called a half reaction, and this is called a half reaction, and this is the whole reaction. So this is the oxidative half reaction, and this is the reduction half reaction. This is the cathode half reaction. This is the anode half reaction. So the anode half reaction is a metal being oxidized, giving electrons away, and then the cathode side is where the electrons are coming to. So the cathode side is the plus side. So if you're looking at a battery and it's got a plus and a minus, the plus side is where the electrons are going to. The negative side is where the electrons are coming from during discharge. So, I mean, obviously, you haven't seen this. This isn't battery that we use. Like nobody's got like a couple of beakers and a salt bridge and they're running stuff off of it. This is the battery that you've seen. This is a typical dry cell battery, a AA, AAA, quadruple A, C, D, whatever. This is what they look like. Carl Gassner made this battery up in 1888. What it is a can of zinc that acts as the structural support, and it acts as the anode, giving the electrons away. And then I've got some basically like cardboardy kind of paper soaked with some kind of metal ion. So aluminum chloride is used a lot. Doesn't really matter. It just has to be a salt. And in the middle, we usually use graphite. So literally the same stuff that's inside of your pencil. And so the zinc produces the electrons. The electrons go to the carbon and change the carbon into something else. This battery has 2 ways to not work. Either the zinc can gets completely used, and that's usually what happens, the interior can, or the moisture that's inside of the dry cell evaporates, because this thing can't be completely closed up. It can't be fully sealed because gases get produced. So those gases need it to have a way to escape. And then the other thing is, if you drop a battery, sometimes this piece of graphite in the middle, since it's literally just the inside of a pencil, if this breaks because it hit really hard, the battery isn't going to function anymore. So no dropping batteries. So the interesting thing about this is you guys probably recognize this shape, right? And we made this in 1888, and we haven't really come up with anything better since then. So Gassner really like nailed this one. Obviously, the battery in your phone isn't going to look like this. That's all proprietary stuff. But it's also because that's a completely different substance, and it needs to be, that one actually does need to be hard sealed. Can't have any anything leaking out of it. Why is lithium a fantastic choice for a battery? It's the top of the activity series, right? If I go down to the other activity series with numbers on it, look at this voltage. If That other battery that we made was, what was it, crappy 0.46 volts. This is 1/2 reaction producing 3 volts of electricity. So if you allow a lithium atom to release its electron, it will also give you 3 volts of electricity. The other thing is if we find lithium on the periodic table and look at its density is 0.54, about half of water. The densities of the copper and the silver, those were huge. So the nickel cadmium batteries, those things are heavy, really heavy. Not that the lithium ion batteries in ours aren't heavy because they need a lot of it. And then there's a lot of extra stuff in there. I don't know if you've seen any of that stuff. Like a Rivian or a Tesla, those cars actually way heavier than regular cars. And have you seen the bad effects with crashes? Haven't seen any of that stuff? Like a Rivian will go right through a guardrail. The guardrail is rated for vehicles that weigh up to about what my truck weighs, and the Rivian weighs about 1,500 pounds more than that. The Ford F-150 Lightning, there's actually one in the parking lot. It's gray. It's the guy who's in charge of instruction, Jarrett. It's his. That thing weighs way, way more than a regular Ford F-150 pickup because of all the battery stuff. So even though lithium is light, you still need a lot of it, and it's still a metal, and it's still got a bunch of other stuff in that battery. So the departments of transportations around this country are trying to figure out how to better deal with cars going off of cliffs and whatnot. Okay, so this lithium ion battery pretty much does everything on its own, right? Does anybody know what the voltage is? We'll just go into this picture. Do you guys know what this voltage is? These regular batteries? We'll just gave it away over there. Each battery's voltage is about 1.5 volts. Maybe a tad bit above that for a fresh battery. So the batteries that are in your remote control, like you got a couple of AAA batteries in there, each one of those batteries is 1.5 volts. If you have a TI-89 calculator, it's 4 1.5 volt AA batteries. That's how it functions. The reason that it's 1.5 is because it's a nominal voltage. The industry all decided that 1.5 would be fine. 4 batteries in an object was good. And the reason they wanted 4 batteries is because the initial calculators in portable objects, all their transistors ran off of a 5 volt, plus or minus 5 volts. So when we became a digital society and transistors became a thing, you needed 5 volts of electricity to turn them on and off. We've since been able to bring that way down, and you know that because your remote control now only needs 2 batteries. And so 2 batteries would only give you 3 volts. So tell me how 2 batteries can generate 3 volts. And it's how the batteries get connected up. So do we see the important part about the orientation of these batteries? These guys are all straight up, right? And their tops are all connected and their bottoms are all connected. Each battery produces 1.5 volts, but because their tops are all connected and bottoms are all connected, this whole thing produces 1.5 volts, and that's it. But this will last 4 times longer than 1 battery. Are we okay with that? But down here, I've got 1.5 volts. So what the electrons do is, looks like I did that backwards. So this gives me 1.5, another 1.5, another 1.5, another 1.5. So those 4 batteries will give me 6 volts of electricity. And that's what all electronics needed initially, was that a minimum of 5 volts to get them to turn on and off, and 6 wasn't enough to break them. So that's what we did. Energizer actually tried to produce a lithium battery, did produce a lithium battery a while, like 20 years ago, and they marketed it in a couple of small towns in the East Coast, and people couldn't figure out how to use them. So they would come as a 2 battery pack. One of them was a battery and the other one wasn't a battery. It was exactly the same, except there was nothing inside of it except a wire. Why? Well, because if this was a lithium ion battery, it produces 3 volts, and this one I would want it to produce 0 volts. So they literally had 2 just so it could make a connection, and you could put these 2 batteries in your remote control. One of them did nothing other than make the connection, and the other one provided all the electricity. But people couldn't figure it out. They would buy 2 packs, they would pull 1 battery out of each, and they'd be both like the dead one, the one that was just a wire, and it wouldn't work. Or they'd put them both in and it would break their remote. So they decided people were not smart enough to use the batteries. So they stopped doing that. Now they do produce lithium ion batteries. You can go to Walmart and buy lithium batteries. But since all of these batteries have to be 1.5 volts, what does Energizer have to do to their lithium batteries? They have to make them half efficient. They literally have a resistor inside the battery that absorbs half of the voltage. So it only produces 1.5 volts. So don't buy those. They're expensive and they're no better. And they're basically a waste. People wanted them, so people buy them, so they sell them. So this is called the parallel arrangement, and this is called a series arrangement. So if you hook things up in series, you can make the voltages build up on top of each other. And if you hook them up in parallel, you can just make it last a lot longer. So if you, my truck has 2 12-volt batteries in it, although the system is all 12 volts. So the 12-volt batteries aren't hooked up in series to make 24 volts. They're hooked up like this. So what they did is they just made a bigger battery with 2 batteries. So the batteries are in parallel to each other. If you rearranged it, it wouldn't actually, the truck wouldn't turn on. You'd actually burn out the alternator if I tried to shut 24 volts through. All right, so in the lab that we're doing today, you're gonna mix different metals together with different ions and see if a reaction occurs. And then you can generate a small activity series. And then you're actually gonna make battery and check voltages using one of those ones that we just showed here in the notes, the voltaic cells. All right, I will see you guys next door.